5.2, we're taking a look at multiplication and division of integers. The majority of what we do in this section is the multiplication component. And let's take a look at what this looks like from the chip model. Okay, so in the chip model, we had those yellow and those red chips. Remember that? So if you have colors there with you, you might grab your colors out so that you can draw this and make it a little bit more authentic looking. And I'll use colors on my screen as well. And in starting, I want to sort of develop for you what this looks like in terms of negatives. If these were positives, we wouldn't have any trouble. If it said 4 times 3, you'd have 4 groups of 3 red chips. Make sense? But we need to figure out, or 4 groups of 4 groups of 3 yellow chips. So we need to figure out what happens when there's negatives involved and how they affect the problem. So we have 2 negatives in this problem, and it doesn't matter which of these perspectives you take, but one of those negatives is telling you have red chips. Shake your head if that makes sense. Remember, red chips are negative. So I'm going to choose to let this be 3 red chips. If you want to let it be 4 red chips at the beginning, that's fine. Okay? But one of the negatives means you have red chips. Clearly, the other negative can't mean that, because what would it look like to multiply negative chips together, like visually? That doesn't make sense. The other negative needs to have another connotation of what it's referring to. And the other negative is actually going to have the connotation of removing. Okay, so if it were positive, we'd be adding things in. If it's negative, we're removing. Okay, so one of the negatives is red chips. The other negative is a removing feature. The number itself is talking about the groups. This is removing 4 groups. So this says, if we sort of read it in words, the way that I've written it, is that I'm going to remove 4 groups of 3 red chips. Okay, is that all right? Remove 4 groups of 3 red chips. So I need to have, some chips. So I'm going to draw our placemat of our chips. And this right here is a placemat that has what value currently? 0. There's nothing in there. This has a value of 0, correct? Now we talked about last time ways that we can keep 0 but still have chips in it. And the way that we did that is we said, hey, if I put these in a pair like this is still the number 0, right? Because this is a 0 pair. So I need to put into this lots of 0 pairs, enough that I can remove 4 groups of 3 red chips. All right, so if I put these in pairs, there's 3 red chips. I should probably be a little bit more orderly in how I'm putting these in so that I can delete them easier later. Whoops. Okay. So there's 0 pairs. I have 1, 2, 3 here. That's still zeros. That's still 0. That's still 0. Well, a yellow chip and a red chip, one's positive, one's negative, make a 0 pair. So at this point, I have in here 12 0 pairs, right? I have 12 reds, I have 12 yellows, there's 12 0 pairs. Technically, you can put in as many 0 pairs as you wish, but I'm only going to need to remove 4 groups of 3 red chips. So this is 1 group of 3 red chips. This is 2 groups of 3 red chips. This is 3 groups, and here's 4 groups. So I've chosen to only put in as many as I need to remove. Okay, so the original circle is worth 0. It's got a bunch of reds and a bunch of yellows in equal amount, so that's why it's 0. And then I'm removing 4 groups of 3 red chips. What does that leave in my circle? Only yellow chips, and Ty's right, there's 12 of them. There's 12 of them. So this is where we end up with, and we have a 12. And it's a positive 12, right? Why? So this is a justification for why the negative times the negative is a positive, but why is this answer positive 12? From the picture.
Because we just have the positives.
Yeah, the red chips were the negatives, the yellow chips are the positives, and the only thing left in my circle is positives, right? The only thing left in my circle is positive chips, so that's the only thing that I've got in terms of sign there. So I have 12 positives that are left. All right, the charged field model looks much the same. It did before as well. It's not a surprise. So this is going to say, again, we're going to remove 4 groups of 3 negatives. So in the charged fields model, I actually have positives and negatives. So they're still occurring in 0 pairs, right? That's the 0 pair, a positive and a negative. Like that. Okay, so the picture looks the same, but I'm going to be removing which ones this time? I'm removing the 3 negatives, but I'm just removing these negatives. So here's 3 negatives, and I'm going to remove them. Here's these 3 negatives, I'm going to remove them. Here's 3 negatives right here, and I'm going to remove them. And here's 3 negatives, I'm going to remove them. So I removed 4 groups of 3 negatives. What does that leave me with? Yeah, all positives. How many? There are 12 positives for an answer of 12. Okay, so this is the multiplication version for our chip model, and then this is our charged field model. All right. The next one is our number line model. And much like, let me pause for just a second, much like this one needed some sort of development of what these values mean, right? What do the negatives mean in this context? The same thing is true for our number line model, okay? So so one of the things we talked about when we did negatives is sort of moving backwards on the number line, right? Or moving to the left. So we have that connotation as well. So this negative here, I'm going to use as being that. You could use the other negative, it doesn't matter. But this is telling us that we're going to move left. So one of these negatives tells you to move left. And since this is a 4, it's going to be 4 at a time. So imagining, sort of like leapfrogging, like jumping 4 across the number line. Are you with me on that? Okay. And then this 3 right here this is the part that's my not favorite part of this particular sort of description. This is telling you that this is the time starting 3, I'm going to call it units ago. If you want to change this word units into hours or minutes or something like that, I'll say example hours. You'll see a really good example of this picture in an example in your problems in your book. I think it's a group work problem, and it talks about the decline in a university's enrollment, and it asks you what happened X amount of years ago, right? In the past, what was it? So you're talking about what happened in the previous however many units of time. So this is some unit of time ago. So what does it look like? Well, it looks something like this when you draw it out. So I'm going to draw in some hash marks, but I'm not going to label them in any way. I'm just going to draw them in for now. I know I'm going to need 12 hash marks because 4 times 3 is 12. So you can go ahead and draw those 12 in there. If you don't end up with enough, you can add more later too. So, but you're going to start on the far right because you're moving to the left, okay? So we are moving to the left 4 at a time. So this is my 1 jump of 4. This is 2 jumps of 4. Did I get that right? Oh, I didn't have enough hash marks. That's what happens. And then here is my 3rd jump of 4. Okay, so I've moved to the left 4 at a time. That's the first description. And then this -3 business says, where was I 3 time units ago? I'm going to say hours because that sounds really awkward. So 3 hours ago. 3 hours ago, where was I? Well, this is where I end. And this question right here is where I began. And I always end in this discussion at 0. So if I ended at 0, where did I begin? I began at 12, right? So this 12 right here is the answer to the question, okay? So let me put some context to this so that it makes some sense, because I think that will help, because this is a really weird one without the context. Let's say that I ate 4 cookies. I ate them, so they're becoming negative, right? They're disappearing. That's my negativeness. I ate 4 cookies, and I did this 3 times. Can you picture that happening? How many cookies were there to start with? 12, right? I ate 4 cookies 3 at a time. At 3 different times, rather. I ate 4 cookies at 3 different times. So I ate 4 cookies at 5, and I ate 4 cookies at 7, and I ate 4 cookies at 9, whatever, like I ate 4 cookies at 3 separate times. How many cookies were there to start with? And it would be 12 cookies. Okay? All right, some details about our multiplication. It says let A and B be integers. So if A is negative and B is negative, right? Then one of the ways to think about the multiplication of these is that A times B is the absolute value of A times the absolute value of B. This works if they're both negative. Okay, we've talked about, we did it a little bit ago, right? Negative times a negative is a positive kind of an idea when we were even looking at the last section of material, right? So this is one way to think about integer multiplication, is that we just have absolute values that we're concerned with if both numbers are negative. Second one tells you what happens if one's negative and the other's positive. Well, if one's negative and the other one's positive, then you end up with a negative as your answer, and then you have the absolute value of the A and the B. And believe it or not, this is really how you think about multiplication. You probably haven't thought about it as being absolute values, but you usually look at this, like the last problem. I'll come back here in a second. We even did this. We looked at this and said, oh, look, I've got a 4 and a 3. I'm pretty much going to be multiplying 4 times 3. We ignored the negatives to get to the number 12 to start with, didn't we? That's essentially what this is saying. It's saying ignore the negatives. And if I'm in case 1, where they were both negative, the answer is going to be a positive. And if I'm in case 2, where one was negative and one was positive, the answer will be a negative. Okay? And you know what? I think we're going to stop right there. I think doing all the properties together later will make sense, so we will pause there for today.